If you get online and look for zero-point energy devices or gadgets or things like that, you're going to find lots and lots of claims, dozens if not hundreds of claims of devices and conspiracies and things that are on the shelf but hidden from us and so on. I don't believe any of that. What I'm presenting to you this morning is, I think, the real McCoy, the real thing. The problem is it's the real thing, but we can't guarantee it's going to work. I mean, this is something that we think may be revolutionary. On the other hand, we have yet to prove it experimentally. So I'll talk to you this morning about the physics behind it. This concerns a quantum vacuum energy patent that Garrett Modell and I reissued a couple of years ago. It's now assigned to the University of Colorado. And it concerns zero-point energy. Now, the zero-point energy comes directly from the Heisenberg uncertainty principle. If you let any oscillator oscillate, it will eventually come to rest because of friction. In the case of a quantum oscillator, it will never come to rest because the Heisenberg uncertainty principle forbids taking the last little bit of energy out of anything. So it was first proposed prior to the onset of quantum mechanics in 1912 and 1913 by Max Planck, Einstein, Otto Stern, who studied this in the context of the black body emission. Now, interestingly, it was sort of dropped from consideration for a number of years until quantum mechanics was developed in the 1920s, and then zero-point energy came directly out of the quantum mechanics formulations at that time, and it's been part of quantum mechanics ever since. You can calculate how much zero-point energy there ought to be at any place in the universe. You do this by looking at the modes of the field. I don't want to get too technical, but modes of the field means in any given direction or frequency, there is an electromagnetic mode. And if you sum all those up, you get a frequency-dependent spectrum that goes as frequency cubed. And so the spectrum of the zero-point energy goes as the frequency cubed, which means it rises very rapidly. Unfortunately, it rises to we don't know where. It could be infinity, which is a bit embarrassing because you don't want an infinite amount of energy in the universe. It could cut off at the Planck frequency, which still is enormously large. So we just don't know where this cuts off, but it goes as the frequency cubed spectrum. Now, there are effects that can be attributed to zero-point energy. One of them is the Casimir force. If you put two plates close together, you find that the wavelengths of light or of zero-point radiation, which is a form of light, that are larger than the cavity, the distance between the two plates in the cavity, they can't exist there because of electromagnetic boundary conditions. And so you have an underpressure. You have more waves of zero-point radiation outside of the Casimir cavity than inside that causes the plates to be pushed together. That's one way to explain the Casimir force. It's been measured. The Casimir force is now a well-established phenomenon. It's not only been measured, but it's also part of microtechnology these days, because the Casimir force is a candidate to use for control of microelectronic devices. It's also responsible for an annoying problem called stiction, which causes things at a very small scale to stick together. So there's no doubt that the Casimir force exists, and that it's even a potentially useful thing or a potential nuisance depending upon how you look at it, but it's certainly something that is part of modern technology. The force between parallel plates due to the zero-point field goes as the inverse square of the inverse fourth power of the distance between them. That's also been measured very precisely now. Now, while I've been emphasizing the Casimir force, in fact, the Casimir force is not necessarily attributed to the zero-point field. It's possible to reformulate all this in terms of the interactions of particles in the two plates with each other, like a typical van der Waals force kind of formulation. And so the fact that the Casimir force exists, even though it seems to me to be a pretty good, more than a suggestion, but less than a proof that zero-point energy exists, it's not a guarantee because there is this alternate formulation in terms of source theory. However, the quantum noise in the circuit has been measured. And in my opinion, the quantum noise in a circuit can be attributed directly to zero-point energy. And so in my view, it has been measured directly as a real phenomenon, that zero-point energy exists. Now, the measurement in the circuits has been at very low frequencies. And so all we know for sure is that zero-point energy exists at very low frequencies. But we need for it to exist at fairly high frequencies to be useful in the context of this invention. I'll be talking about the device that we hope will be able to tap into zero-point energy. Now, the objection is also raised sometimes that you can't actually extract energy from the zero-point field. It can't do anything useful. Well, there's actually a thought experiment that was published in 1984 already by Bob Forward that shows very clearly that, yes, you can get work out of the zero-point field. There's no doubt about it. It's not useful in this context, but you can get work out of it. We're hoping what we proposed is useful. This is not useful, but it's a demonstration of the principle. If you take this this sort of spiral plate, and you charge it up with electricity, so it simply has positive or negative charge on it, and you then rely on the Casimir force that acts between the layers of the plates. You can use the Casimir force to press this spiral together, and in doing so you're increasing the electric field in the region. Well, you're increasing the electric field because you're causing the charges to get closer together. And so this is very useful for demonstrating the effect of the zero-point field doing work on this device. Now the problem is it can only do work during half a cycle. If you wanted to recycle this, you'd have to pull it apart again and let the zero-point energy then push things back together. That's not very useful because it's going to take more energy to pull it apart than you get out of pushing it together. But think of this as an engine that works for one half of a cycle. Not useful, but certainly demonstrates that zero-point energy is doing work. It actually does work here. And that's the useful aspect of this. So this was the Robert Forward battery experiment proposed in the mid-1980s. Now, the basis of our experiment, or our patent, is the prediction from theoretical physics that the ground state of hydrogen might be attributed to the zero-point energy. Now, we all know that the classical view of an atom that was developed in 1913 to try to explain the early results of atomic physics showed that there was a problem in the Rutherford view of the atom, which was having the electron orbit around the nucleus just like a planet around the sun. The problem with that, of course, is that as an electron goes around the nucleus, it radiates energy, a lot more radiation. And it would quickly spiral into the nucleus, and boom, that's the end of the atom in less than a millionth of a second. So clearly that model is wrong. But what's been discovered since then, in the 1970s and 80s, was that if you let an electron spiral around the nucleus, just the way a planet would around the sun, yes, it will emit a lot more radiation, but if you let it pick up energy from the zero-point field, you find, interestingly, that there's a balance between those two effects exactly at the Bohr radius. So this strongly suggests that the Bohr radius is not there because Bohr said you are not allowed to decay. Rather, at that point, there's a balance between the amount of energy that a radiating electron will naturally emit as it orbits around the nucleus versus what it would pick up from the zero-point field. And so we're kind of back to a classical view of an electron as something that is sort of real, that's going around a nucleus, that is stabilized in its orbit by zero-point energy. Now, I don't want to take that too literally, because I'm not really very happy with the thought of going to a 100-year-old model of the electron going around the nucleus. But the point is that zero-point energy contribution to the stability of whatever this orbit is exactly balances the emission that you would expect if this were a classically orbiting electron. So there you have a schematic of it. The stable orbit in quantum theory is provided by simply the Bohr condition that you're not allowed to radiate, whereas in our case the interpretation is one of a balance between two things: radiation and emission, radiation of emission and absorption of emission from the zero-point field. So in quantum electrodynamics, you have a prediction of zero-point energy, but it's regarded as virtual. And electron energy states are determined by the wave function. So what you see down here at the bottom is the classical, or I must say classical, sort of classical quantum probability density distribution of the electron orbital as a function of distance from the nucleus. Now, as it turns out, you can go a step further than the previous Hal-Puthoff analysis that I showed, which indicates that at the Bohr radius, there's a balance between the emission and absorption of radiation. You can actually go to simulations that show that if you let an electron sort of be buffeted around be buffeted by the zero-point fluctuations as it orbits around the nucleus in a Coulomb field, that in fact this probability distribution, which is attributed usually simply to the wave function of the electron, can be reproduced by letting the model of the zero-point field buffeting the electron take place. And so here's a simulation run by Dan Cole at Boston University. He took a classical electron, let it orbit in a Coulomb field, let it be buffeted by the zero-point fluctuations, and looked at the position as a function of time of that electron, and lo and behold, it looks just like the probability density function that you get from quantum mechanics. And so it looks as if this model, this sort of simplistic model of an orbiting electron, does a pretty good job of giving you the same important condition that you find from quantum mechanics. Just a close-up of the same thing. The quantum probability density function for the ground state of hydrogen is a solid line, and the simulations using the buffeting of the zero-point field on the electron is the dashed line. This is also reproduced by L.J. Nickish at an institute in Monterey, who did the same thing but with his own simulation program, different from Dan Cole's. So, what is the basis for our patent? Well, in SED, electron orbits are determined by this balance of emission and absorption. And so, if you take an electron, an atom, I should say, and put it into a Casimir cavity, what you see here in the middle, is the long wavelength radiation, schematically represented by everything in green, and shorter wavelength radiation from the zero-point field represented by everything in purple. And when the atom is sitting out in free space, of course, it sees the entire zero-point radiation field. When we insert it into a cavity, that cavity then blocks out the longer wavelength aspects of the zero-point field, and so it's only reacting to the truncated zero-point field, which is represented by the purple arrows. And so since there's less zero-point energy pumping up the electron in its orbital, we would assume that the electron would spiral inward slightly, and as it does so, give off some energy, which energy then we would propose to capture. And so this is the basic idea behind the patent. So the idea is that if you have an atom, and let's have it moving from left to right through the system, in free space, you might have an atom that has a number of electrons. In particular, probably we would use noble gases, argon, neon, xenon, or krypton, because they have a number of outer shell electrons that can be acted upon by this effect. In free space, you have several electrons in the orbitals you'd expect. When the atom enters a Casimir cavity, so you have plates here, the orange lines represent plates, you would then expect some emission of radiation from the atom because the orbit has shrunk a little bit. Then the atom moves out of the region between the plates into free space again, so this gray represents no Casimir plates. It's again pumped up by the zero-point field, goes back into its normal orbit, goes through another Casimir cavity, and so on. So you can have this take place many times. In fact, in one of our prototypes or prototype concepts, hundreds of times, the atom would move through in and out, in and out, in and out of Casimir cavities, and each time it does so, it would emit some radiation that we would hope to capture. So where's that energy coming from? Well, in fact, the energy is always picked up when the atom leaves the Casimir cavity. It's being picked up from the universe at large. We're drawing energy out of the zero-point field of the universe. It's sort of like taking a thimble and taking water out of the ocean. Yeah, we're getting energy at the expense of something, but it's something enormous, something vast. It's something that permeates the entire universe everywhere. And so the view is that we are able to tap into this universal sea of zero-point energy using this device. And down at the bottom, we simply have a schematic representation of a heat exchanger. We don't know exactly where the radiation is going to come out and how to capture it. That's part of the problem we face now in trying to show experimentally that this is going to work. Capturing emitted energy. It's oftentimes argued that we are making a mistake by assuming that there's any energy to be captured, because as the atom is pushed into the cavity and again is pushed out of the cavity, somehow we're tapping into that energy that we're hoping to capture to move the atom. And I don't think that's the case, because take, for example, an ordinary hydrogen atom, and we have it in the ground state. So we have an atom of hydrogen in the ground state. There's the electron. We illuminate it with ultraviolet light. And by illuminating it with ultraviolet light, we cause an excitation of the first level. So this is the Lyman alpha transition at 1216 angstroms. And so we have an excited atom. And if we then have that atom enter into a region where there's an opaque shield, not a Casimir cavity, just something to block out the ultraviolet light, then clearly the electron will drop down into its ground state orbit again, emitting Lyman alpha radiation. And then it'll move out again, and if we want to, we could repeat the process. Now, it does us no good because we're supplying the energy to do this. But the point is that just because the atom is emitting energy in this region here where the excitation radiation is being blocked, that's got nothing to do with any pressure gradient needed to push the atom out. And so this is an analog, a very simple analog of what we're proposing to do with zero-point radiation. So I see no reason why there should be, and the analog is shown down here. In the case of zero-point radiation, instead of ultraviolet light, you have the zero-point field. You have Casimir plates that block out the zero-point field in the same way that these opaque shields block out the ultraviolet light. there's an emission of light or whatever radiation, form of radiation. We don't know at what part of the spectrum it will come out. And then upon reemergence, again, we expose it to the zero-point field and it's re-energized. Could this be tested apart from, well, there are two ways, of course, to test this idea. One is to actually have energy generation take place in such a device. Another test would be a spectroscopic one. And there are a couple of ones that I've thought about that I think would work. One involves looking at a transition, an outer shell transition of xenon-1, which is a noble gas. The ordinary transition between the outermost excited state and the unexcited orbital is known to take place at 1469.6123 angstroms. That's a well-known spectroscopic data point. What I'm suggesting is we took xenon-1 and put it inside a Casimir cavity. Both these orbitals would be influenced, would be modified to some extent. It's unlikely they'd be modified in exactly the same way. And so there's probably some differential between these two orbits. And so we would expect to measure a spectroscopic line at 1469.6123 plus or minus delta angstroms. So unless we happen to be extremely unlucky and have the effect, have the zero-point field effect occur exactly the same for both these orbitals, there should be some differential here. And so this spectroscopy experiment would show whether in fact orbitals are influenced by the zero-point field the way we hope. The problem with this is that you'd have to do it in vacuum because this radiation is at 1400 angstroms. You can't do it in air, you have to do it in vacuum. That's difficult then because you have to put all your instrumentation into a vacuum chamber and so on. There's a simpler way to do it. Do it with hydrogen because you can do the same trick. In this case, we're looking at the Balmer lines of hydrogen. The transitions from the n=3 to n=2 state, 65, 63 angstroms, one of the most well-known lines in all spectroscopy or astrophysics. And again, we would expect to have a differential effect between these two orbitals so that the Balmer line would be shifted to 65, 63 plus or minus some delta A in angstroms. Now, this is simpler because you don't have to do this in vacuum. You can do this in air. The difficulty is that hydrogen is not monatomic. It naturally comes as a molecule. So you have to dissociate the hydrogen and at the same time excite the hydrogen molecules and then look at the cascade, the recombination spectrum, to see whether such a shift takes place. So this is a second spectroscopic test that doesn't suffer from the vacuum chamber requirement, but then suffers from the fact you have to dissociate the hydrogen molecules and excite the resulting atoms into the state where you have then a recombination that at the end will give you a Balmer spectrum line that is shifted because of the effects of the Casimir plates. So the way to do this on a large scale would be to build, for example, plates that have metallic strips put on them so that the atoms would flow through Casimir cavities. You see that here's a Casimir cavity. And I just cut the top plate off so you can see the inside of this thing. So the gas flow would go this way, crossing Casimir cavities, in and out, in and out, in and out of Casimir cavities. And a device like this can accommodate 1 million or more Casimir cavities. It's very simple to build such a device. Another one might be like this, a stack of conductor and non-conducting layer plates with Casimir tunnels on the order of a tenth to 1 micron in diameter. And again, the atoms would simply flow through, in this case, a tunnel that consists of many, many thousands of Casimir cavities. Each time it passes into and out of a Casimir cavity, we would hope to pick up some energy. And another way that, in fact, if Larry Lemke's in the room, I'll thank him for this. Another way to do that is to have a rotating device that looks very much like a CD, a stack of CDs, and the rotation of this will naturally pull gas through it. And as the gas then flows down the center and out through along the discs of course have Casimir cavities etched on them, you again get the same kind of effect. So there are various ways to do this, and we're hoping that this will be a new energy source. If we're correct, this is a game changer. I mean, it would be a free energy source. It would change things dramatically. On the other hand, we've yet to demonstrate that the effect actually occurs. We have these good theoretical reasons to think it does, but theoretical reasons are one thing and experimentation is something else. We hope to fabricate a prototype. Garrett's been working on this. We did have some funding for a time from DARPA, and the results from that were inconclusive. There was also some private funding, and the experiment is still going on at a very low level here at the university. We need another several $1 million to do this right, to do this properly. And the design is based on microchip technology, which Garrett tells me and told all of us last night is pretty easy to do and pretty cheap to do. So the cost of building one of these things, if it works like this, would be very, very low. And we're hoping that this demonstration can be built here at the university and show the effect, and that this then becomes a game-changing result that emerges from within the SSE, let's put it that way. And I think I'm done.
Do we have time for just a few questions?
Bernie, you didn't say anything about the material. Is that the Casimir plates? Can it be metallic or?
Yeah, it's got to be metallic. It's got to be conducting.
They have to be conducting.
They have to be conducting. They have to be conducting at the right wavelength too. Because if you go far enough into the ultraviolet, materials lose their conductivity. So that is another issue. We're sort of in a narrow range where there has to be, the cavity has to be a certain size, and yet if we go down to that size, we may be stretching the conductivity properties of the boundaries of the plates. So it gets a bit finicky and a bit tricky. But Garrett will solve all that.
Over here. Does it, the effect gets stronger as you get smaller dimensions, right? So is there a point at which you could make this a smaller scale device and get more energy, or is there sort of a trade-off?
It does, yeah. And if the theory is correct, then the electron, when it loses sort of the support of the radiation at one wavelength, it drops down into a lower orbit, and that then is stabilized by the higher energies of the zero-point field. So the further it drops, the more energy comes out in principle, yes. Yeah, that's right, yes.
You and last night you talked about the size and how much energy you're going to get.
Yes.
It isn't clear to me you know how much of that energy you're going to be able to capture.
Yeah,
and
it's really...
how can you make these estimations without knowing that?
It's a swag. I was assuming that we get perhaps 1 electron volt per transition of an atom through the cavity. In the case of hydrogen, the ionization is 13.6 electron volts. And so I'm assuming we get something like a few percent of the energy of the ionization, a few percent of the effective ionization energy from a given level. But it is a swag, it's a guess.
Okay, it's clear that this talk has generated lots of questions, which we won't have time for at this time. Hopefully Bernie will be available at the break.
I'll be around.
And later. So thank you again.